Yeah, so over the next hour and a half, I will be going through the Bebras competition. So pretty much what we're going to do a quick overview on what it is, the test structure, what it is about, and then we'll also do a couple of questions relating to this so that you have a good understanding on what this is all about, right? So first of all, I'll just go ahead and give a quick overview of what this competition is. Now, one of the big companies in Australia, the Australian Maths Trust for different competitions, has recently introduced this as part of its sort of program. And so even though this competition has been around for many years, this is going to be more and more popular from this year starting onwards, just because they have sort of taken over that sort of job, right? Now, what is the Bebras competition? Now, it is a 15-question challenge. And the main topic of it is going to be computational thinking, and it is going to be held for students in year 3 all the way to year 12. Now, in terms of who can compete, it's basically just going to be anyone, right? You can see that over the past 581 schools have competed in this challenge in 2023, and over 30,000 people, students, did it last year as well. Now, just like the Australian maths competition, this is going to be split into different year groups, which is like year 3, 4 for middle primary, year 5, 6 for upper primary, and then 7, 8, 9, 10, 11, 12. And each of these will have their own different little test paper. And they also have the unique times as well, right? Where year 3 and 4, they get 45 minutes to do the test and 60 minutes to do the test for year 5 and 12. Now, if you look at the key dates over here, you notice that we have a round 1 and we have a round 2. Basically, this competition is going to be held twice a year. So we can sort of think of this as a competition which is bi-yearly, or it's going to be, yeah, I'll go ahead and stop the annotations. So there's going to be a new competition every half a year. And this is going to be held within like sort of 3-week time period. So for the first round, it's going to be between 23rd of April to the 9th of May. And you might think, oh, well, I thought it's going to be 60 minutes. Why is there a time date over here? Now, how that basically works is that between these two dates for the first round, you get to start at any time between these two dates. And you just have 45 minutes or 60 minutes to complete these 15 questions, right? Depending on what year group you are. And it's going to be the same thing for round 2 as well. So you can sort of think of them as 2 separate tests. They aren't really going to be related to each other, right? So the delivery is also going to be online. So you can basically do it anywhere. And the reason why it's online is because there's going to be multiple different question types, which we'll go through later. I'll just go on to the next page. So first of all, there's going to be multiple choice questions. There's going to be questions where you have to type in a number or words or an equation. And there are also going to be interactive question types, which we'll go through later. And this is only made possible with an online format, right? So if you think about every other test you do with pen and paper, it can only circulate multiple choice option, which is A, B, C, or D. But then in this case, we'll see how the questions may differ and the different ways we can answer them. Yes. Do you have a question, Kevin? Oh, sorry, I think you're muted right now. I still can't hear you, so maybe you can just type your question in the chat and I'll go ahead and read it later. So I'll just quickly go through what the question answer format is as well. So of the 15 questions, right, the total number of marks is going to be 135, and these are going to be split based on 3 sort of difficulty levels. There are going to be easy questions, there are medium questions, and there are hard questions. Now, this is just what they're called. It doesn't necessarily mean that hard questions will be hard and easy questions will be easy, but they sort of determine the marking scheme of the question, right? So easier questions will have less marks. Medium questions will have more marks, probably are going to be more difficult, and harder questions, more marks, right? If you leave anything unanswered or incorrect, you don't get any marks for it. And this is going to be the award criteria as well. So all of these are already going to be set in stone. So it just depends on how well you do, right? If you get everything correct, you get the excellence award. And if you get between 114 and 134, you get high distinction and so on, right? So in the test, I believe there's going to be 5 of each of these questions, if this adds up to 135. And we'll go through what each level of difficulty will be like for year 5 and 6 especially. So do we have to go to a specific website? I believe for the registration, it's either your school or you can go to the website, and then you can probably get more details of it later. But for today's sort of seminar, we're just going to be going through what this test is going to be like. Now, next thing I'm going to talk about is what type of questions are going to be in this test. Since this is going to be very different from what you learn normally at school. So what is this idea of computational thinking? So computational thinking involves skills used to solve problems and design systems. Now, this is very broad, but they're basically the skill sets needed for people to work in the computer science industry, working with computers, algorithms, stuff like that, especially with technology and data. And in terms of like some of the jobs relating to this sort of computational thinking area, it's a very fundamental skill in something like software engineering, like artificial intelligence, machine learning, even finance, and much more than that, right? Now, in terms of the Bebras competition, they sort of have 6 rough categories on what they test you on. So we have decomposition, pattern recognition, abstraction, modeling and simulation, algorithms, and evaluation. Now, individual questions won't be just one of these. Usually there's going to be a mix where like a question might test you on your decomposition, pattern recognition, and algorithms, stuff like that. Now, I'll go ahead and go through what each one of them is about. So I'll just go through and read through each one. Decomposition, breaking down problems into smaller, easier parts. A lot of the times when you approach a question, it's going to be very big and complicated. So what do we need to do? We can break it down into smaller chunks, solve each of these smaller chunks, and then hopefully we're able to sort of get a bigger picture, find a pattern, and use that to solve whatever more complicated question we have. Now, pattern recognition, like I said before, it's just noticing patterns and applying them. This is going to be pretty straightforward, which you'll see later on when we go through some of the example questions. Abstraction is just taking out any information from a question and turning it into something that's useful. And as like a very, very basic example of like abstracting a question would be like, oh, if I have 10 apples and I eat 4 of them, how many apples do I have left, right? This question is basically just what is 10 minus 4 or 10 minus 6, whatever I said, and nothing to do with apples. And the other 3, modeling and simulation algorithms and evaluation. Normally, these are going to be dealing with following a set of rules and applying them over and over again. Again, we'll go through more of these later on. So does anyone have any questions so far before we get into any of the examples? So as we go through the examples later on, I'll go ahead and tell you what is going to be the level of difficulty of the question and what is going to be the question type as well. So the 3 main areas we're going to go through in terms of the examples are, first of all, we'll go through questions relating to pattern recognition. We'll also go through questions relating to networking. We'll understand what this is going to be later on. And the last sort of area we'll go through is going to be coding and decoding. Note that there are going to be lots of other topics in the Bebras competition. So let's go ahead and have a read through the first question, which is over here. It says it's an easy question and it's also an interactive question type. We'll see what this means as we read through it. So the question says, mark a path from the beaver to his home, and you can click on one arrow at a time to make the correct sequence and show the path home without creating any loops. So this is going to be a fairly straightforward question. We have the starting point over here. We want to get to this end point, and we have to follow these arrows to form a straight line to from the bottom left to the top right. And in terms of why this is an interactive question type, because this is on a website, all of these little arrows here are going to be clickable. So in the end, you're just going to be selecting these arrows, all of these until you get to, you selected all the arrows to form a path to go from the start to the end, right? So again, is anyone confused on what this question is about and what it's trying to ask you to do? All right, so what you can do for this question, you can probably just jump straight in and try and highlight some of the paths you might make to do this question. So you can do it sort of randomly, like, oh, looks like we'll probably have to use this path here, and then we have to use this path, or I can go up, or I can go to the right. What happens if I go to the right? I go up and up, or I can go left, or I can go up. And if I go all the way up, it looks like I reach a dead end. So you can see that there's going to be a lot of paths here, which you can click and go through, but a lot of it isn't going to be correct. So like, what is the approach to solving this question, right? Is there a way which we can get the answer without doing a lot of this random guessing and checking? And the answer is, yeah, there's a couple of different things we can do. So yes, so one of you pointed out, one of them is just going to be working backwards. So starting from the home, what are the paths which we must take to go back, right? If you look, if I zoom all the way in, we'll see that, well, looks like we have to be taking this path. If I work backwards again, it looks like we have to be taking this path. And then what other points will lead to this point here? Looks like I have to take this path, and then I'll have to take this path because I don't want to repeat this. And if you keep working through this, eventually you will be able to get your answer, sort of why this is going to be on the easier question type. And this is going to be one of the algorithms we use to solve this question. It's just basically working backwards. So I'm just going to continue going along. So looks like we have to take all of these paths like that. If you work all the way back, eventually you will form a path like that to get from the start to the end. In terms of how long this will take, probably a couple of minutes. So these are the questions which you should be getting correct. And another solution to this that's not working backwards is to identify what we call black holes. So a black hole would be an example like this, right? Where we have three arrows all the way, pointing all the way to one point. So we can never reach this point, right? Because otherwise we can't get out and we can't get to our destination. What that means is I can't be using this route, or this route, which means I can't be sort of going here. This is also like a mini black hole. I can't be using this route. So there's going to be a lot of different arrows which we aren't able to use. And by identifying all of these black holes, what you do is you eliminate all of the pathways which we can't use. And eventually we're going to leave very few options to an actual path which we can get, right? So by doing that, you can still get to the same answer. Now, on the next page, I have written out the solution here. So you see that the correct solution is what we had before, where we go right, up, left, up, and doing that. And one way of solving it is to, like I said, identify the black holes, which are drawn in this diagram here, and places which lead to these black holes. And another way is to just to work backwards. So how is this sort of related to computational thinking? So in the field of computer science, the idea of finding a route is going to be very important, especially in algorithms. So you can think of this as like Google Maps, right? If I'm going from one point to another point, what would be the fastest way to go from this point to that point, right? This is going to be an example of a route finding and why it's going to be very useful in real life. So we're going to go through another question. And this is also going to be a pattern recognition question. It's going to be a little bit different because it's going to require a couple of calculations as well, right? So just going through a variety of different questions. So Beaver Bert has a long strip of colored paper for a party. This strip has three different colors, yellow, red, and blue, in a regularly repeating pattern. And Bert's friend James has cut out a section of the paper as shown in the diagram. James says that he will give back the missing piece if he can correctly guess the size of the piece cut out. How many colored squares does the missing piece have? Right, so how many squares does this missing block have? Now, in terms of the difficulty, this is going to be medium level, which just basically tells you how many marks this is worth. It's worth 9 marks, and it's also going to be multiple choice. So on the screen, you just have to select one of these, and that will be your answer, right? Now, for this question, would anyone like to have a guess? How often does this pattern repeat? If you want to call it out.
33.
3. It repeats every 3 spots. So we have yellow, red, red, blue, yellow, red, red, blue, yellow, red, red, and so on. What you'll see is that it repeats every 4, right? We have this group of 4, and then we have this group of 4. So we're sort of breaking the question down into these smaller parts, yeah. And if we know that it repeats every 4 like this, if I assume that the yellow, red, red, blue is a 4, this yellow, red, red, blue is another 4, and then we have yellow, red, red, and then the missing piece, and then we have something red, blue, and then another piece over here. So there's only a couple of different things which we can fit in here, right? So how would we work this out? We actually have to use a little bit of maths. Now, if I find a smaller sequence which can fit in between, it would be yellow, red, red. And then in terms of the missing pieces, we can have blue, yellow, red, and it looks like we can join it up with red, blue again, right? So over here, we could technically have 3 pieces missing, and then we have this 4 repeating pattern over and over again, right? But with our options, 31, 32, 33, 34, none of these is going to be 3. So like, what is going to be our correct answer? So if there's not going to be 3 in the middle, we have to have another set of 4 inside of it, right? So it has to be 3. I'll use a different color. It has to be 3 or maybe 7 or maybe another 4, 11, and so on, right? So the final answer we want is we just want any number which is going to leave a remainder of 3 when I divide it by 4. If I were to generalize this, it's going to be any number in the form of 4 times x plus 3, right? So x is going to be any number. Or I can just ask myself and go through the options, through the process of elimination, which of these numbers is going to give me a remainder of 3 when I divide it by 4. And that one is just going to be 31, right? So does everyone sort of understand the gist of this question? Yep. So in terms of why we would be using abstraction for this question, it's because this question isn't actually about these banners, right? These colors, yellow, red, red, blue. We were just trying to make it into a repeating sequence of 4 and then find how many are going to be over here. We changed it into this form of the number of things missing is going to be in the form 4x plus 3, right? Because it has, if it repeats every 4, and there's going to be at least 3 more than that in between, it will be in this form. So yeah, we go ahead and move on to the last pattern recognition problem here. And this is going to be a hard question, right? So the hard question, not necessarily meaning it is hard, but it's just going to be worth more marks. And a lot of it is going to require a bunch of reading to understand what is going on. So that's sort of the abstraction part of the question. So let's have a read of this one, flipping cards. A row of cards is laid out in front of you. The cards may lie face up or they may lie face down. And for each step in the game, we have to go through these rules and steps. So this is also going to be very common in the Bebras competition where they give you a set of rules and then you just have to follow them and go through them one by one. So examine the cards from right to left. If the current card is facing down, so like this, we turn it face up and we stop. If the current card is facing up, so like this, we turn it face down and we move on to the next card. And when you run out of the cards, you stop. And as an example, let's say we have this sort of pattern over here, and we go through each of these steps. This is just going to be one step here. So the first card is face up, so we turn it to face down. Second card is face up, we turn it to face down and we move on. The third card is going to be face down, so we turn it to face up and then we stop, right? That's going to be one whole step. And in the test, they actually allow you to experiment with this, where you can actually turn over each of these cards if you want. And there's also a reset button to turn all of the cards face down again. Now, this question is going to be multiple choice, and it's asking, how many steps will it take to make all of the 7 cards face up? So how do we approach this question? One of you did say, is it binary? That is going to be one of the solutions, but let's try and break it down a bit first, right? So a couple of different topics of the Bebras competition: decomposition, pattern recognition, and abstraction. So if you remember, decomposition is just breaking it down to smaller parts, right? Rather than working with 7 cards, let's just work with 1 card or 2 cards or 3 cards. If I'm just trying to flip 1 card over, that's going to take 1 step. If I try to flip the next 2 cards over, it's going to require another 2 steps, right? If I try to flip the next 3 cards over, it's going to require another 4 steps. And you might be realizing a pattern over here. We're going from 1 to 2 to 4. If you continue onwards, it's like, well, I need to flip another 3 of these cards over from face down to face up. So everything here, including this spot here, will be another +7 or +8, right? So in order to get to this spot where 4 cards are going to be facing up, we're going to need another +8, right? And this is already enough to do the question where to get the first card, we just need 1 step. To get 2 cards flipped over, we need another 2. To get 3 cards flipped over, we need another 4. To get another 4 cards flipped over, we need another 8. And we just continue on, right? +16, +32, +64. And I believe that's your answer because we have 1, 2, 3, 4, 5, 6, 7 cards in total flipped over, right? And this is the pattern recognition part where we're trying to find what is this pattern here. Pretty straightforward because it's just doubling each time. And as for the abstraction bit, we are just turning these cards into a different form, face down, face up, right? Now, a lot of you have mentioned that it is a binary pattern as well, and that is going to be the better solution to this question. So I'll go through that as well, where essentially we can represent the face down and face up cards as 0s and 1s. So if I look at this card pattern for the before, it's going to be represented by 0, 0, 0, 1, 0, 1, 1. And this as a binary number would be, if you know a bit of binary, 1 plus 2 plus 8, right? So as a number, this number is going to be 11. Now, afterwards, the new binary pattern is going to be 0, 0, 0, 1, 1, 0, 0. And this is going to represent 12 in binary, right? So essentially for each step we're just changing the binary number to 1 more than what it currently is, right? So the new question becomes, how many moves are there to go from 0, 0, 0, 0, 0, 0, 0 to 7 ones, right? Which is all face down to all face up. So 0, 0, 0, blah, blah, blah. That's going to represent 0 in binary. 1, 1, 1, 1, 1, 1 is going to represent 127 in binary. And the number of steps is going to be 127, which is why the answer is going to be this over here. Over 100 steps, but less than 1,000 steps. Binary is going to be a very important concept in the field of computer science. You might have heard how like all computers run on are 0s and 1s, which is technically true. But it's also how we represent numbers as well for computers. So computers will recognize a 12 as a 0, 0, 0, 1, 1, 0, 0, or something along the lines of that. So This question isn't going to be particularly too hard either, right? Even though it is worth 12 marks, if you were able to sort of know this binary trick, we can get this answer very, very quickly in a couple of minutes and get all 12 marks. So just by selecting the correct answer, you either get all of the marks or you get none of them. So there aren't going to be any partial marks for this competition as well. And that's going to be the case for a lot of these questions here, where there's a couple of different theories and tricks which we can use to do the question really easily, which if you didn't know, it might take a lot more time. So I guess, does anyone have any questions up to this point of this sort of presentation here?
Excuse me, Andy. May I ask the questions you listed there, which year group is that for?
This is for years 5 and 6.
Thank you.
But I will say that for particular questions, they will be in multiple age groups. So they may be in the 3-4 paper, maybe in the 7-8 paper as well, right? But they might just appear as a different difficulty. Okay, so the next concept we're going to go through is going to be this idea of networking. Now, even though the topic is networking, it should be graphs, right? And I'll talk a little bit about graph theory as well. So I'll have a read of this question first. And then what I'll do is I'm going to go through a little bit of content relating to the structure of these problems and some of the theory behind it. So the diagram shows the relationship between 7 students in a book sharing club. The names and ages are shown. So we have this sort of structure where we have a bunch of dots and circles connecting these dots together. And the club has some regulations for members. When you receive a book, you read it, and then you pass it to the youngest friend who has not read it yet. If, however, all your friends have read the book, then you should pass it to the friend who gave it first to you. Now, Ben gets a book, and we just want to find, if he shares it with everyone, who will be the last person to read this book. Now, this diagram is something which is going to be very common in not only the Bebras competition, but in computational thinking and computer science in general, right? So I'll go over what all of this is going to be about. So the idea of graph theory. So basically in graph theory, it's just going to be a diagram of dots connected with each other. You might have seen different diagrams like this before, right? So this is going to be what we call a graph. Now, a graph is going to be made up of 2 things. One, vertices. The second thing is going to be edges. Now, sometimes these have different names as well. So vertices can also be called nodes. And the vertices will be these red circles over here. And the edges are going to be what connects them, right? So why is this useful? It is used to represent a lot of different things. For example, even for a train line structure, you could say one of these is going to be a suburb like Hornsby, another one would be Chatswood, another one would be Central or Epping. And all of these are going to be connected by these paths and can be represented as a graph, just like over here, right? Where we have these graph sharing pattern, where different people and lines connecting to them are going to be their friends. So in graph theory, these edges, they have different forms, right? Sometimes they are going to be weighted. Sometimes they're going to be unweighted. So what does this all mean? Whether a vertice or node is going to be weighted or unweighted. It just means that there is going to be a weight to it or a value to it. If I were to change this graph up a bit and assign values to each of these, then this will now become a weighted graph. Now, where is this going to be useful? Now, this could be representing the time it takes to maybe get from one suburb to another. So if this was location A and this is location B and this is location C, how long does it take to get from location A to B? It'll be 5 minutes. How long does it take to get from location A to C? It'll be 3 minutes. And this is where the weighted graph is going to be useful. And we'll probably come across an example of this later on. Another thing about these graphs is that they could be directed or undirected. Pretty much with each of these edges, they could have a direction. For example, what if I can only go from C to A, but not A to C? What if I can go from A to B and B to A? So this is what a directed graph means. Now, a lot of the questions in the Bebras competition, like I said, is going to come in this form over here, where we use this sort of a structure to ask the question. Now, I'm going to go through the answer of this book sharing club question now. This one isn't going to be too hard either. So what we're essentially doing with this graph is we're going to be searching through each of the vertices of this graph, right? So we're starting with Ben over here. And we want to essentially visit every single one of these graphs, every single one of these points, a very important concept in computer science, right? So if I follow this algorithm, what this is saying is I need to pass it to the youngest friend. But if I don't have anyone else to pass it to, I need to pass it back to whoever gave it to me. So who is Ben going to pass the book over to? So his youngest friend is going to be Ted, right? So it's going to go this way here. And now Ted is going to read the book. So I'll mark that as red or highlight it as green. Now, who is Ted going to pass to? Now, his friends are Bill, Anna, Sarah, and Kim. Looks like Ted is going to pass it now to Anna. If you follow these steps, it's not going to be very hard as long as you keep track of which person has given it to who. Who is Anna going to pass it to next? Well, it's going to be between Bill and Sarah. So it's going to be Bill. I'll go ahead and write out this arrow, and then Bill can only pass it to Tom, right? Ted has already read the book, so we're going to be visiting Tom next. And then Tom has two friends, Bill and Ben, except they've both already read the book. So we have to do the case where we pass it back to someone who gave it to us. Tom gives it back to Bill. Bill gives it back to Anna. Anna is going to give it to Sarah now because Sarah has not read the book. And if we continue this on, eventually we're going to get to this pattern here, and Kim is going to be the last person to read the book, and that's going to be our answer, right? So this idea of trying to traverse a graph is going to be a very big topic in computer science, and a lot of a big algorithm is called a depth first search, where essentially we are trying to travel to the deepest point. And then once we've sort of reached a dead end, we keep traveling to the next point. And yeah, this is going to be the algorithm we're following in order to get to our final point here until we visited basically everyone. So over here, I wrote that to represent networks, computer scientists use graphs as data structures, which are simply sets of connections. And to analyze these graphs, there are multiple algorithms that evaluate different properties. And one of them is going to be the depth first search, which we actually just did, right? Even though we didn't really know what we were following, what all this was a depth first search. And the main takeaway is that a lot of questions are going to be using this idea of a graph theory. So I'm going to go through another question, one more question relating to these networks over here. And it's going to be this one here. And this is going to be a hard question, or it's going to be labeled as a hard question, which just means that it's going to be worth 12 marks. And it's also going to be interactive as well. So let's have a read through this question here. An internet service provider wants to set up a new network. There are 7 cities which have to be connected so that every city can send and receive messages from any other city. And the company has to pay to set up links between cities, and the costs are shown on the links between the cities below. So we can sort of see another graph network where we have a bunch of vertices connected by a bunch of edges. And these edges are going to be weighted as well this time, right? We have a value assigned to each of these edges, unlike the previous question, which there were no weights. So how would we go ahead and approach this question? right? There are so many different combinations which we can use. Like, oh, we could connect these two together. We could connect these two and then these two maybe, and then like maybe these two. But how do we know which solution is going to be the best solution, right? When there are so many different possibilities. And this is exactly what the question is asking you. Modified Dijkstra's algorithm with one city as the base. So we actually do not use Dijkstra's algorithm, which one of you pointed out. So this is a very famous algorithm, which essentially what it is even though not as related to this question, it's how can we find the shortest path from one vertice to another vertice? But in this case over here, we're actually go through a couple of different concepts. We're going to be going through what we call a minimum spanning tree. So what is going to be a minimum spanning tree? What this is that it's going to be the set of vertices and edges, which is going to have the smallest edge value when added together, but it's also going to connect everything together, right? So for example, if I make a very, very simple graph here of these 3 points, 1, 2, and 4, what do you think would be the minimum spanning tree of this graph here? What's the fewest number of edges I need to connect all of these 3 points? This one's going to be pretty obvious. We're going to need this edge here, and we're also going to need this edge here, right? We can see that these two are going to be connected via this new edge. And what the minimum spanning tree is just whatever is going to be the set of edges that gives us the smallest value. So how do we find the minimum spanning tree of a graph? We actually use a algorithm called Kruskal's algorithm. So over here, I wrote that we use an algorithm called this. You don't actually need to know what the name is, but the idea is we follow this rule over here where we're selecting the smallest value that joins a new point. So let's go ahead and run through this algorithm here, right? If I look at this graph, what is going to be the edge which forms the smallest value? This was also taught in the computational and algorithmic thinking competition as well. The smallest value which we can join is going to be this point over here, right? This one that connects this point and this point. Now, this is what we call a greedy algorithm because we are going to be selecting the best possible answer at each step. So I know that this has to be the best way, the best connection, because there is no cheaper way to go to connect these points together, right? So if we constantly find the cheapest ways to connect a new city together, eventually everything is going to be connected via the cheapest way possible. So by following this algorithm, we select this first edge. What is the next value we pick? Or what is the next edge we pick? This one over here, right? And now we have 3 points connected. What is going to be the next value we pick? The 2. And now we have 4 of these cities connected to each other. I believe they are cities. Yes. And if we keep following along, the next smallest value is going to be 3. And we connect another city like that. The next smallest value is going to be 4. What you'll see is that they're actually connecting these 2 cities, but what we have is we're going to have 2 of these different structures. They're not going to be connected yet. So we don't actually have the minimum spanning tree just yet, right? The next smallest value is going to be 5. And if we connect that to each other, that's going to be what the final answer is. Now, this is going to be an interactive question because each of these little edges are going to be selectable. Once you have selected these 3 answers, there's going to be a button which you can use to save your answer. And that's going to be enough to get all of the marks, right? Now, This question, like I said before, it was labeled as hard, but if you were to know this algorithm here, then it's going to be really, really easy, right? It's something you can do in maybe like 1 to 2 minutes just by selecting the smallest value at each point. So this is going to be another question where if you knew this algorithm here, it's going to be really easy. But if you didn't, then it's hard to think about where to start, right? So does anyone have any questions up to this point so far? If there's anything you want me to go back to, then you can go ahead and message me. Or if there's any questions you want to ask, you can go ahead and text me as well, right? So yeah, we've gone through a variety of different questions relating to this idea of graph theory. Note that there's going to be a lot of other different algorithms as well, which are going to be very helpful when doing the test, right? So the last and final thing I go through is going to be the idea of coding and in decoding, right? So for a lot of these different questions in the Bebras competition, they actually go through a lot of different of these computer science coding language and terms where we have these if then else statements. We also have loops as well. And we have to be able to understand how to interpret these and how to form them ourselves, right? So just like with the graph theory, I'm going to go over a little bit of the theory relating to this as well. And I'm going to be just going through two different things, the idea of conditionals and the idea of loops, right? Now, these on its own are going to be very basic concepts. So what is a conditional? A conditional is basically just means if something is true, we want to do something, right? For example, if the weather is sunny, then I want to go outside, right? This is going to be a conditional because in order for me to go outside, I need this to be true, right? And this is going to be the general form of these conditional statements. If something, which is a statement, then something, right? So very basic concept. But a lot of the times, this won't just be like sentences. There'll sometimes be numbers like, oh, if this number is greater than this number, then I want to add one to this number, right? And so on. Now, something else about these conditionals is that it's not only if this, then that. Sometimes we have, if this isn't true, then I want to do something else. And this is where we come across the term else, right? So the three main key terms we'll come across when doing these conditional statements is if, then, and else, right? So if I were to continue this example, if the weather is sunny, then I want to go outside. But if the weather is not sunny, I want to stay home, right? And that's going to be the structure of this conditional statement, right? We'll see this example in this question over here. Let's just have a read through it. So after the school, the young beavers often play together. To avoid quarrels about where to play, they throw a normal six-sided die, and the decision is found according to this rule here, right? So if the first throw is greater than the second throw, then we go to the woods. Otherwise, we have this over here, right? And then we enter another conditional. So like, how do we read through this? These can be represented in different ways, like a flow chart, but often you can just think about these statements one by one, where I want to check this first. If it's true, I go on to the second statement. If it's not true, I go on to this block over here. What next? I have another conditional. If this is true, I go on to the second statement. Otherwise, we go into this, right? And we just need to find which sequence of throws will leave the young beavers to the sports field. So this is going to be a multiple choice question. And it's also going to be medium difficulty as well. Like I said, the difficulty just determines how many marks it's worth. It doesn't necessarily mean it's going to be very difficult, right? So we essentially want to go to the sports field, which is going to be this over here, right? Now we can ask ourselves and work backwards, how do we get to this block over here? If the throw is greater than the second throw, do we want this to be true or not? We want this to be false, right? If it was true, we would be entering this green statement over here, but we want to enter this purple block. So if the first throw is greater than the second throw, I want this to be the opposite. Yeah. So does anyone want to have a go at trying to find what is the opposite of the statement here? First throw is greater than the second throw. What would be the complete opposite to the first conditional? Yeah, no name. All right, someone has also messaged me smaller than or equal to. Yeah, exactly, right? So we want the first throw to be smaller than or equal to, or equal to the second throw. So first throw is smaller than or equal to, so we could have this one. This one is also smaller than or equal to. This one is not smaller than or equal to. This one is smaller than or equal to, right? And then you sort of get the idea. We're going to enter this next conditional. We want this one to be false, right? Because we want to enter this else statement. So the third throw is less than the first throw. If I want that to be true, I want to find the opposite. I want the third throw to be greater than or equal to the first throw, right? So greater than or equal to, which I'll just write the symbol. The first throw greater than equal to the third throw. We want this one to be true. It looks like of all of these, only this one is true, right? So here we have the correct answer. So yeah, this is pretty much just testing your ability to work through and understand these if, then, else statements. So does anyone have any questions for this one here? Yeah, the first answer is correct. So the next thing I want to go through is going to be the idea of loops, right? So whenever we have a lot of repetitive tasks, we can just turn it into a loop. So as an example, let's say I want to add 1 to 10, a total of 4 times, right? So what would this sort of look like in terms of like coding language, right? It could be something like this, where I want to repeat 4 times, add 1 to a number, right? The reason why this is a loop is because we're doing the same thing, but we're doing it multiple times. And I'll give an example of the different types of this. So a very popular loop is going to be this sort of repeat statement where we specify the number of times we want to do something, right? So repeat this 2 times, repeat this 10 times, repeat this 1 time, like repeat 4 times, move forward, or repeat 3 times, move to the right. Now, in terms of what we're repeating, we can be repeating multiple steps, right? For example, if I had repeat 4 times, go up, and then go right. What would all of this look like? I want to go up, and then I want to go to the right a total of 4 times. So that's once, that's twice, that's 3 times, and that's 4 times. That's essentially what this is going to be useful for. It's going to be a lot simpler than doing go up, go right, go up, go right, go up, go right. And this is where this is going to be useful. Now, I'll go through an example of where this might sort of pop up. So this question is called short-ish program. So the mini computer here shown on the right drives a triangular robot. And following these instructions, the robot drives in a small square twice and ends up back where it started. So it's going to be this here, right? And the problem over here, we use 5 blocks of code, 3 purple, 1 green, and 1 gray here. Now, basically what the question is asking you to is try get this robot here from this point over to this point using 12 blocks or less. This is going to be a easy or hard question. I think this one was only worth 6 marks, which is technically an easy question, but I'd say it's one of the harder easy questions, right? So first of all, let's understand what all of this means, because this sort of thing is going to be very common in the Bebras competition. There's almost always one of them in each of the competitions held twice a year, right? So if I repeat this 8 times, I go forward twice, and then I turn right. I go forward twice, and then I turn right. So that's going to be doing it 2 times. Forward twice, turn right. Forward twice, turn right. So this is me completing it 4 times. If you imagine me doing this 8 times, it would be doing this loop a total of twice. And the question is, how can I use these blocks to get from the start to the end over here, right? And I'm only going to be restricted to 12 blocks. Now, for this question here, I'm actually going to go to the question itself and show you what it is going to be like for that question and what you might see in the actual exam. So I'll go ahead and share my other screen. So over here, just ignore most of the tabs. The mini program, computer program shown on the right drives a triangular robot, blah, blah, blah. And what you have is you have this sort of space at the bottom to sort of run through each of these things. For example, if I were to move forward a total of 3 times, I could drag this here, move forward, and then put 3 over here. And if I press run, looks like I move forward twice, but then I hit a dead end. So the question is, how can I use these 4 blocks to form a path from the start to the end, right? And you sort of get all of this time to sort of run through all of these. So maybe I move forward twice, and then I turn right. What happens if I do this 3 times? If I run, I go up, then right, then down. So, and then go back. So looks like if I go up, right, down, I end up here like this. But now I need to turn left. Go this way, 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 this way. So you can imagine that, oh, I can complete this whole thing using 20 steps, but we're only restricted to 12. So we have to sort of use this repeat sign over here. So I'll talk about how we can break this down into smaller parts. First, before I type in my answer. So going back to this page, just so I can sort of draw it out. Does anyone think they have an idea as to what path we might want to take for this over here? So where would we have to go? Starting from red. What would be a nice repetitive pattern which we can use? So to sort of simplify it a bit, I'll say moving forward is F, turning left is L, moving right is going to be, turning right is going to be R, right? So if I were to sort of break it down, I can sort of see there's a bit of a snake zigzag pattern, maybe something like this, right? Now, how would I make all of this? Looks like I need to go forward twice, and then I need to turn right. So forward, forward, and then turn right. And then I'll go forward, forward, and then I turn right, and I go forward, forward. This is gonna make me end up at this spot over here, right? But if I keep repeating this, I'm just gonna do a loop. Eventually, I will have to turn left, and it's gonna be at this point over here, right? I need to be turning left. If I continue this on, forward, forward, turn left, and then I'm at this point, but I'm facing up, and you sort of see that, oh, looks like I need to go up, up, turn right, 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 turn right, and so on. So if I break this down into these smaller steps, you see that there's going to be a lot of these which are going to be repeating, right? If I were to write the whole thing out, looks like we need to do another forward, forward, turn right, forward, forward, turn right, forward, forward, turn left, forward, forward, turn left, and so on, right? And it's always, before you do the Bebras competition, it's pretty important that you have a bit of practice on how we can form these different algorithms using this sort of structure over here, right? The next question we go through is also going to use this sort of thing, but we're going to be introducing another piece to it, the if and else statement block. So how would we go through the answer? Essentially, finding the bits that repeat looks like forward, forward, turn right, repeats, forward, forward, turn left, repeats. And then we're sort of repeating this entire block again. And we actually need to do this again, right? If I continue this block onwards and onwards, we're going to just be doing the zigzag pattern. Now, how would I construct this using all of these little things? I'll actually go back to sharing my screen on the computer. So if you remember, we want to go forward twice. So I'll connect these two together and then turn right. So this, some of you might find this pretty fun as well, since it's like a little problem which you use. And if I sort of repeat this 10 times, you see that, oh, we're doing this loop back and forth. But I only do want to do this twice. So I'll put the 2 in over here. And what was I doing next? I need to move forward twice. And then maybe turn left. What is this going to do? So looks like I need to be doing this twice. So to do the answer, this is essentially what you're going to end up with, right? Where this block makes you go up, right, down, and then to the right. And looks like we need to do this a couple more times. So we need to repeat this whole block again because we're essentially starting out at the same position, but shifted all the way to the very right. So if I put this entire block in another loop, we can actually get to our answer, right? And this is going to be the final solution. It doesn't actually matter what this is, but the point is that we need to repeat this twice, and put this loop within another loop, right? Yeah. So going back to the other screen, you sort of understand, what is the sort of question that's going to pop up for all of these, right? So I'm going to go through one more question. And for this, we're going to see how the if and else statements work as well. All right, so last question here for coding and decoding before we get into like any extra questions and the overview of the whole thing is that write a program that takes the robot to the green square, and your program must be made using blocks of 4 or less, right? So we can move forward, we can turn left, we can move to the right, and we have the for loop, which we had gone through before. So I would highly recommend like working through some of these questions before the exam. That's going to give you a huge head start. It means you don't have to figure everything else on the spot, right? And you get to save a lot of time, which we'll learn how to do. Now, we also have this new block here. If there's a path ahead, then we want to do something. Otherwise, we want to do something else. So this is going to be a conditional block, right? So the question is, how can we get from this red square to the green block using 4 blocks or less? So it's like one path you could make is maybe move forward a total of 1, 2, 3, 4 times, turn left and then move forward 1, 2, 3, 4 times, right? But then this is going to use way too many blocks, right? So we actually want to use this if statement over here, where we want to keep moving forward until we hit a wall, in which case we turn left. And if there's no path ahead, I keep moving forward until there's a path ahead. Otherwise, I need to turn left, right? So the final answer which you will have, which I'll just sort of reveal to you, is going to be in the form of this. If there is a path ahead, so pretty much if there is an empty block in front, I want to move forward. Otherwise, I want to turn left. So this is going to be the conditional where we have, if this is true, we want to do this. Otherwise, we don't do this, right? But if I only sort of do this once, I'm only going to be going 1 block, right? If I do this twice, I'm going to be going 2 blocks. So what we want to do is we want to wrap this entire thing with another repeat. So another of those loops. So I want to repeat this many, many times until I get to this green block. And you can sort of imagine how we can get to the answer, right? Does that make sense? So let me know if you have any questions for this. So this question over here is actually going to be considered a hard question. So it just means that it's going to be worth 12 marks of year 5 and 6. On average, you'll probably have around like 4 to 5 minutes to do each of these questions, especially this one here. I'll go ahead and go to the actual website for this question or the example question for this one here. So how can I go from this red dot to the green dot, which is what I had before? I want to repeat this statement where if there is a path ahead, I want to move forward. Otherwise, I want to turn left. Let's see what's going to happen if I run this. I hit a block, I turn left. I hit a block, I turn left until I get to the end. And this is essentially the answer we want, right? So I would recommend being very comfortable with this sort of working out before this sort of a structure before you do the Bebras competition. So that's pretty much going to be all of the example questions I want to go through today. So now I'll go ahead and ask if you guys have anything to ask about either the Bebras competition, any of the topics we went through, or the topics related to this. I'll also note that since this is sort of new to the Australian Maths Trust, you'll notice that within the summary page, way back over here, the cost was free as well. So there's no reason not to do this since you don't actually lose anything, right? So this is free for pretty much everyone to do. All right. So during this time, feel free to message me anything you want to ask. Otherwise, I'll do like final quick sort of summary of what we just went through today. So main things about the Bebras competition is that it's going to be 15 questions, right? So normally knowing the format of any test is very important, of which we're going to have 5 questions which are going to be easy, 5 of them which are going to be medium, and then 5 of them which are going to be hard, right? So the easy questions will be worth 6 marks. Medium questions are going to be worth 9 marks. And then hard questions are going to be worth 12 marks. So you see that everything sort of adds up where we have, well, there's 15 questions on average, it's 9 marks. So 15 times 9 is going to be 135 in total. How do you practice the coding questions? So I will be able to like find the resources for those questions, and for those I can let you know. There's going to be a lot of questions relating to that where you can sort of try out a bunch of different problems. Yeah. All right. So yeah, continue along. If you're year 5 and 6 above, you're going to be given 60 minutes to do the entire thing. On average, that does mean 4 minutes per question, but easy questions, you can probably spend less time. Harder questions, probably going to take more time. So all of this sort of balances out, right? In terms of the question types, which we had, there were 3 different question types. We had the multiple choice, we had the integer input, and we also had the interactive question types, which has a range of different things, right? So just be aware of that. They're going to be pretty obvious while you do the test. And in terms of the main topics we went through, first of all, remember we went through the pattern recognition questions. Other thing was to do with networks and graphs. And the last one was going to be on coding and decoding. So for pattern recognition, we went through how we can change the question up into a different form and then find patterns based on that. For networks and graph, we learned about how it's going to be formed, the vertices and nodes. And there's going to be algorithms relating to that. And like Kruskal's algorithms, there's also other stuff. One of you mentioned Dijkstra's algorithm, which is finding the shortest path from one to the other. And we can go, there are also a lot of different concepts relating to that, such as minimum spanning trees and more. And finally, the idea of coding and decoding. It's very important that you understand how we can work with these conditionals and loops and how we can combine both of these together to sort of complete a task. In this case, in these 2 questions, it was just navigating this little robot from the start to the finish, right? So yeah, I guess, does anyone else have anything they want to ask? So I think that's going to be all I have to present for today. Basically, what is the Bebras competition, some of the question types and topics as well. So if you don't have anything else, then I guess I'll see you guys maybe in the future. Right. Yeah. And in terms of what the lessons would be about, it's going to be going through a bunch of these different topics and algorithms used to solve these questions, right? Yeah. Right. So thank you all for coming and listening.
Okay, thanks, Andy. So guys, just we can take a probably 10-15 minutes question time. Do we have any questions want to ask? Anyone want to volunteer ask question? You can either voice it or you can text it to us.
Yeah.
We just say, is anyone want to ask questions? Okay, no question, it's fine. So if that's the case, I would like to thanks everybody and thanks Andy for the nice presentation, well prepared, and for everyone attend the seminars. If like anyone interested, please contact Dr. Jin Education for further information. All right, otherwise I would close out today's seminar. Thank you guys, good night.
Thank you all.
Cheers, thank you all, bye-bye.
Bye.